New pictures got by the James Webb Space Telescope have shocked scientists. Rather than becoming our view of the universe, these pictures uncovered an upsetting reality. Our continuous cognition is missing to make sense of the chance of the universe in its beginning stages, where the speculation of the universe's beginning stage shows up at its cutoff points. This drives us to consider new speculations about its early phase. The inquiry emerges with respect to how the universe was shaped in detail, and why this new discovery challenges even the most experienced space experts to sort out more about the Big Bang and the ever-evolving subtleties of the discovery. We should evaluate the chance of the Big Bang itself, rather than popular thinking. The Big Bang was not an effect in earlier space. Rather, it was space itself that began around 13.8 billion years ago, alongside matter and time, from an exceptional trademark in genuine science and cosmology. A quark describes where gravity is momentous to the point that the bend of spacetime becomes endless. Today, following billions of years since the start of the universe, we see that our divine home is part of a huge collaboration. For specialists, this addresses a fundamental piece of the universe since its very existence. Its incessant evolution is critical to comprehend the universe isn't meandering into earlier space. Rather, space itself is persistently filling in size, as shown by traditional speculations. The first stars started to shine somewhere between 200 and 300 million years after the Big Bang, marking the finish of the so-called Dark Age. This was the point at which the first brilliant, magnificent objects bunched together to form mature systems. However, how rapidly these universes developed remains a continuous secret. An enormous piece of information arose through the first pictures received by the James Webb Space Telescope in July 2022. Specialists reported that the telescope had identified different worlds, some of which had existed around 300 million years after the formation of the universe. However, compared to the divine designs that formed billions of years later, these early systems were significantly more modest and less gigantic. This fits impeccably with the scientific model accepted by specialists. The density of matter in the youthful universe was simply not enough to prompt universes the size of those noticed today. This began as the discovery of 6 astonishing redshifted brilliance spots from James Webb, which eventually set off quite possibly the most significant cosmic emergencies of recent times. Although these newly found cosmic systems are similar in age to recently recorded universes, they are almost as large as our own Milky Way galaxy. This has created an interesting mystery in Big Bang cosmology. Later, looking at a series of pictures received by the near-infrared camera, specialists identified the previously mentioned light sources using redshift. Trained professionals confirmed that the light from these objects required more than 1 billion years to reach our eyes on Earth. Consequently, we are dealing with structures that had already existed somewhere between 570 and 700 million years after the confirmed Big Bang. By examining the characteristics of these plans, it was concluded that the Webb telescope had captured 6 early cosmic systems in the picture. Shockingly, these cosmic systems were so large that they defied traditional cosmological assumptions. Rather than finding the usual dwarf galaxies, structures were identified that were nearly as vast as our own Milky Way galaxy, despite having formed early in the universe's history. Assuming that we continue to analyze the data gathered by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly unimaginable 10-billion solar mass mark. However, whether this possibility is considered, the mystery is not completely settled. Even in this scenario, there would be far more massive mass in the early universe than previously expected, presenting a puzzle. The identified objects challenge almost all conventional cosmological speculations. Even if, by some stroke of luck, one of these galaxies turns out to be real, it would challenge our past assumptions. To make sense of the existence of these structures, the density of matter in the early universe would need to be several times greater than previously accepted. Another, equally peculiar explanation relies on the likelihood that these galaxies formed in a manner that is still completely unknown to us. These revelations and the discussions they are raising will prompt further assessment of the theory of the Big Bang. Many space specialists with alternative perspectives are frustrated, and their viewpoints are frequently heard in scientific journals. Even those who express doubts about existing theories are often marked as improper or extreme. However, It is clear that even specialists who still defend the theory of the Big Bang are constantly confronted with unanswered questions. These questions include specific issues like why and how, 13.8 billion years ago, something literally rose out of nothing. Might something truly begin from nothing? Or was there some triggering event? Or was it all just an accident? Stephen Selling pointed out that the nature of time, as far as we understand it, began with the Big Bang. Consequently, this process could not have been triggered by something else or by an external cause. A similar uncertain question relates to the consistency of radiation and density throughout the universe. Regardless of which direction or at what distance we look on a larger cosmic scale, we find similar densities and distributions of systems, nebulae, and radiation across the universe. Modern scholars explain this phenomenon through the theory of cosmic inflation. However, different specialists extend this assumption further with a theory of turbulent expansion. According to this idea, expansion has only ended in certain regions, like bubbles, and continues immeasurably elsewhere. This suggests that different universes could form in these bubbles, each with its own unique physical laws. In this model, an inevitable question arises: what if the universe doesn't represent the total whole? More specifically, what if another universe existed before our own? In this case, the Big Bang would become part of a larger cycle. According to this viewpoint, our universe is part of a larger, more intricate structure. Within this model, the chance of an everlasting pattern of breakdown and revival of the universe is advanced. However, this is not the only perspective presented in the field of cosmology. Aside from the theory of how things came to be, in 1955, for instance, an article appeared in NASA's Big Time, suggesting that there might never have been a Big Bang, since the universe has existed for an infinite period. In this view, the expansion of the universe would be non-existent, and the consistent development of matter could give the impression of steady evolution. Another fascinating, questionable hypothesis comes from the area of quantum physics and string theory. Some tests have suggested that our universe and everything in it could be a projection or a higher dimensional simulation. While this may sound like the plot of an eccentric sci-fi film, it could be related to the Kesef scale, which measures the level of advancement of a civilization based on its ability to harness energy. If there were a Type 3 civilization capable of fully using the power of an entire galaxy, it might have created an ideal simulation. However, determining the truth of such a scenario is a highly complex matter. Investigating the depths of cosmology and the origins of our universe leads us into a space of significant mystery and ongoing scientific inquiry. The new pictures captured by the James Webb Space Telescope have reignited debates about the very fabric of our existence, testing established theories and provoking researchers to reevaluate fundamental aspects of cosmological understanding. At the heart of this inquiry lies the theory of the universe's origin, a foundation of modern cosmology. According to this theory, around 13.8 billion years ago, the universe rose out of an exceptionally dense and hot state, expanding rapidly and resulting in the spacetime and matter we know today. This giant event was not just an explosion within prior space. It also incorporated the earliest beginning of space itself. The idea of a phenomenon where gravitational forces are so intense that the curvature of spacetime becomes infinite supports our understanding of this early vast epoch. Yet, the discovery of early systems by the James Webb Telescope challenges our assumptions about how quickly structure formed in the universe's earliest stages. These galaxies, identified within a few hundred million years of the Big Bang, appear surprisingly developed and massive when compared to current cosmological models. One of the key questions raised by these discoveries is the nature of cosmic inflation. According to the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand radically. This rapid growth would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, recent discoveries suggest complexities in the early universe's development that may require changes to inflationary models. The formation of galaxies like those seen by the James Webb Telescope forces cosmologists to reconsider the circumstances and processes that governed the universe's early history. These galaxies, now massive and large so soon after the Big Bang, suggest a density of matter that exceeds previous estimates. The mystery grows when considering how such large structures could form and evolve in such a short, infinite time. Furthermore, The discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy content. While dark matter is believed to provide the gravitational framework necessary for galaxy formation, the distribution and properties of dark matter in the early universe remain unclear. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang view. Some theories suggest that our universe is merely one of many in a vast multiverse, each with its own unique physical laws and constants. These ideas, emerging from advances in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One theory gaining momentum is timeless inflation, where universes continually arise from a larger expanding space. This theory suggests that our universe could be just one bubble among countless others, each with its own set of physical properties. The challenge lies in finding observable evidence to support such speculative ideas, as they stretch the boundaries of observational approval. Another provocative hypothesis posits that our universe exists within a simulated reality, akin to a computer-generated simulation. This concept draws parallels to advances in artificial intelligence and computational science, where simulations can mirror complex systems with remarkable fidelity. If true, our perception of reality as a distinct physical universe could be fundamentally altered, raising significant philosophical and scientific questions about the nature of existence. Moreover, advancements in observational astronomy continue to reveal the immensity and complexity of the universe. Telescopes like the James Webb Space Telescope, with its exceptional sensitivity and resolution, promise to uncover even more secrets of the universe. Future observations may shed light on the earliest moments of the universe, offering clues about its ultimate destiny and the fundamental principles governing its evolution. Beyond observational cosmology, particle physicists are investigating the essential particles and forces that shape the universe. The mission to unify gravity with the other three fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, remains a central goal of theoretical physics. Models like quantum gravity and string theory offer potential frameworks for understanding these critical interactions at both the smallest and largest scales of the universe. In the realm of quantum mechanics, the concept of time itself remains a subject of intense debate. Quantum theories propose that time may be evolving or even subtle at the fundamental level. Understanding the nature of time within the context of cosmological models could reshape our understanding of the universe's origins and development. Additionally, the search for extraterrestrial life continues to captivate the public imagination and drive scientific inquiry. The discovery of exoplanets, planets orbiting stars outside our solar system, has expanded our understanding of planetary diversity and the potential for habitable conditions elsewhere in the universe. Future missions, such as the James Webb Space Telescope's examination of exoplanet atmospheres, may provide evidence of biosignatures indicative of life beyond Earth. Furthermore, scientific pursuits and philosophical reflections on the universe enhance our understanding of our place within it. Questions about the meaning of existence, the possibility of intelligent life elsewhere, and humanity's future in space exploration continue to drive exploration and discussion across disciplines.